So now we want to make this intuition rigorous. So to analyze this, let's define geometric mean. Geometric mean of a random variable y. Let's write g of y. And let's say y is always positive. And if y takes, say, values a1 to as with probability p1 to ps, then we let geometric mean of y be the multiplication of ai to the pi for all I from 1 to s. I mean, equivalently, you can say that this is same as the exponential of the expectation of log y. Then what do you want to do is we want to prove we want to prove that the, say, claim is that permanent of A is at most the geometric mean of L. And then we want to also prove that this geometric mean of L is the number that we have we have in the statement. So we want to show that these two. If we know these two, then we find the upper bound for this permanent. And how do we compute these two? Is using some sort of double counting. So we have these two permutations, sigma and tau. And once we count in a way that we fix tau and then we vary sigma and then we count once. And the other time we fix sigma and we count tau and then we compute. So double counting is usually the way that there are some, in philosophical level, it's like there are some arrays and you count the things column by column and add together, and then you count the things row by row and then add them together, and then those two should be same. By making them same, you prove something. So that's the double counting. Again, you have many choices of sigma and many choices of tau, and then you fix one of them, and then you compute, and then you add them together, and you do that in two different ways to conclude. So let's prove this claim first, that the permanent is at most the geometric mean of this random variable L. So how do we do it? We will do it by fixing tau first. We want to first show that if we have this inequality with fixed tau, meaning that if we prove permanent of A is at most G of L, conditioning on tau being some tau 0, then we can actually deduce the original statement of the claim. Indeed, why we can just fix tau is that if we know that once we fix tau, then this geometric mean is bigger than or equal to the permanent of A. If we know that for any permutation tau 0, then what do we have? The geometric mean of L is nothing but a product over all tau sub 0 that G geometric mean of L conditioning tau equals tau 0 with the probability that tau equals tau 0 as an exponent. And we know that this inequality holds for every one of them. So this is same as, it's at least the permanent of A to the probability of tau equals tau 0. And this is permanent of A, summation of probability that tau equals tau 0, which is permanent A to the 1. So we conclude the desired inequality. So we can fix tau. So we fix tau. And by reordering rows, we know that if you reorder the rows, it doesn't change the permanent, so we can do that. So by reordering, we can assume that tau I is actually I. Tau is the identity permutation. If you have several rows, you just change the rows accordingly so that you have tau 1 to tau n in order. And let's also reorder the columns. Again, by the same logic, we can reorder the columns without, changing permanent. So this is just for convenience on writing. So we reorder the columns so that, assume that the first row has ones in the first, say, R columns. So we have this matrix which looks this way. And how are we going to do it is we will use induction on n. When n is 1, this claim is obvious. And we assume that the claim holds for n minus 1. And then we want to prove that it also holds for n. So for each j, let tj be the permanent of A with first row and jth column removed. So again, we choose one of them and then we delete this first row and delete this column. Then remaining matrix, you compute the permanent and then let that be the Tj. Then this Tj is exactly the number of sigma in S with sigma 1 equals j. So that's, almost by the definition of S and the definition of permanent as we have observed before. And let's say T be the average of these T R numbers. Then what do we know? Permanent of A is summation of Tj, which is RT. So Now we condition on sigma 1 being j. Then the multiplication of numbers r, let's write it this way, r2 to rn is our estimation for permanent of A2. So A2 is the matrix we get after deleting first row and jth column. So that's A2. Then what do we know? If we apply induction to this specific matrix, so this is the matrix we obtain by deleting first row and then jth column. Then geometric mean of R2 to Rn, which is say L prime for this matrix. So assuming sigma 1 is j, and we compute R2 to Rn, then that's same as you initially consider this specific matrix, and then compute the values of R in there, and then values of L in according to this matrix. So that's exactly this geometric mean of this conditioning on this. Because conditioning on this is same as just deleting these two. So this is by induction, at least Tj. So by induction, we know that this is at least permanent of A2, which is Tj that we have defined as the value of Tj. Then what do we know? Geometric mean of L is same as multiplication of j equal 1 to r, geometric mean of this value, where this is j, and then probability that it actually happened. Then because of this induction, you can, this induction hypothesis, you can replace each term here into give me a moment. R Tj sorry. This is RTJ because we know that R1 is R. Because, and this number is TJ. So let me rewrite this. So we know that this is R1 times this to this number. Okay, this is correct. Because L can be computed by using R1 and then the multiplication of the rest. And we know that this R1 is always R. Because when we delete the first row, we assume that there are exactly R many. So this is RTJ. And what's this probability? Probability is same as Tj over S. because the probability that we choose this is, you choose uniformly at random among all S. Among all S, there are exactly Tj many permutation with the, sigma 1 equals J. So this is the probability. And we know that this S is same as RT. So this is same as you pull out all the R term. Then R to the summation of Tj over RT is same as 1. So you can pull out R completely, and rest of them is Tj to the Tj over RT. And you can actually show that this is at least R times T to the T over 1 over T is RT, which is the permanent of A as we define the T to be. And here, this inequality holds because we know that the function x log n is convex. If you have a convex function, then you take if you have a convex function, you have two values, say x and y, then the average of fx plus fy is bigger than the f value of the average of two value, because the first average here and second average here, so we know this. By using that, and this function is convex, so we can actually show that the average of some of the values is bigger than the just putting the average, which is t log t. So this is as big as this. So you take the exponential, then what do we get? If you take the exponential, then this becomes tj to the tj over r product, and this to be t to the t. So that's how you get this and this. So this proves the claim. Now we are left to show this equality. As mentioned before, now we want to prove it in double counting kind of way. So here we fix to prove the claim. We fixed tau and then we estimate. But we can also fix sigma and we estimate. Now we calculate this GL conditioning on a fixed sigma while not fixing tau. Again, this fixing is okay because this computation, we can just change this tau and tau 0 to sigma and sigma 0, then everything is fine. All these computations, with the equality here now, because that's what we are claiming, then we can actually, not this permanent, some number that you would get. Let's say that if we know that this is equal to some number m, then this becomes m, and this becomes m, and this becomes m. So the entire geometric mean is m, where this is actually sigma. So it's okay to fix sigma, and then we just show the equality that we want here. So again, for the convenience of notation, we reorder columns so that sigma I is I. For all I. And how does tau is selected? As tau is selected uniformly from Sn, the columns 1 to n are deleted in order. And the order it's deleted is uniformly over all n factorial possibility. Meaning that the all n factorial possibility of order of deletion happens with the probability 1 over n factorial. So for some I, so let's say J1 to JRI be the columns such that each column contains 1 in its ith row, and J1 to JR minus 1, JR sub I is deleted in this order. What it means is that if you have a matrix and then in this ith row you have these 0 and 1, and then first you say, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. You do your process. You delete the tau 1, say here, and then you delete this. Then J1 is 7. And then you choose tau 2 and you delete this. Because this doesn't contain any 1, so 8 doesn't satisfy that this condition that it's ith row, it has 1, so we don't do anything. And then we choose say 1, and this is deleted, and this is 1. Now you let the say 2 is 1. And then you delete say 3, then say 3 is 3. So J1 to J sub Ri is the order of those columns which is deleted, but we ignore the columns which doesn't contain 1 in I. Then these are the, again, random variable which is determined by this tau. Then our Ri is the exactly number of, So here we have I, meaning that at certain, say, else time, we decide to delete this row. So that's R tau L, which is Ri. And we, at this moment, we want to count the number of ones remaining here, and then we write this. That's Ri. This Ri is S. If we have this J Ri minus S plus 1 equals Si, which means, so we deleted 7, 1, 3, and 7, 1, 3, say 4, 6 in this order. Give me a moment. And let's say I is 3. We know that because at the ith time, what do we delete is when tau L is 3, say I, we will delete sigma tau L, which is same as tau L, which is I. Because we already fixed sigma as an identity permutation. At this time, we will delete ith row, ith column. So this is the situation. So here we are about to delete this ith row. Is exactly at right before we get this, we delete the third column. So if it's on the third time, then R I is 3. Because these two are gone, so we don't have any 1 here, we don't have any 1 here, but the other 3 are left. On the other hand, if this order was different, say 7, 3, 1, 4, 6, then at the time of deleting the ith row is at this time, so R3, so R3 is 4 in this case. If this order was, say, 1, 6, 4, 7, 3, then R3 is 1. So it depending on which ordering we have. So if I is on this sequence at this place, at specific place, then you count the number of remaining ones, 1, 2, 3, 4, then that's the number. So Ri is, say, 4 exactly in this case, if J sub 5 minus 4 plus 1 equals I. So J 2. If this is at the second place, then this is 4. So we have this. But what have we just discussed? So we have discussed that this tau is electrically uniformly from the all set of permutation. So these columns are deleted in order uniformly over all n factorial possibility. So this ordering, every ordering 1, 3, 4, 6 to 7 to 6, 7, 6, 4, 3, 1, all of this 5 factorial ordering is equally likely to obtain. So as columns are deleted in order uniformly over all n factorial possibility. The probability that this Ri is S, in other words, this I is deleted at certain place, is 1 over Ri. So this I could be within this in same probability. So this could be the first one, or this could be the second one, this could be the third one. Those probabilities are all same. Hence, what do we know? The geometric mean of Ri is, so it could be 1 with probability 1 over Ri, and 2 with probability 1 over Ri, all the way up to Ri with probability 1 over Ri. So let's say logarithmic of this is summation of j over Ri. J is 1 to Ri, which is logarithmic of j. So which is 1 over Ri times logarithmic of Ri factorial. So by using linearity of the expectation, we know the expectation of logarithm of g Ri sum, let's say summation of logarithm of g Ri. No, let's not write it this way. Yeah, let's just expectation of so logarithm of geometric mean of L is same as summation of 1 over Ri logarithm of Ri factorial summation over all I. Hence, what do we get? The geometric mean of L is same as multiplication of Ri factorial to the 1 over Ri over all I runs from 1 to n. So all the GL so far we have written is actually GL with the sigma equals sigma 0. So by applying this argument, we can actually compute that the actual GL is this. This together with the claim that it acts as an upper bound for the permanent finishes the proof. So we have proved this Bregman's theorem, and in the next video let's see some simple application that we can get from this.